models are wrong, but some are useful. This is a mathematical model using actual data. It does not mean that it is entirely correct, but it may be useful. So there are three main groups of this impact. So the first one is government, obviously. So this is a tool that allows government to make policy decisions for mitigation effects. So that includes things like border closures, mask mandates, etc., etc. The next is the community. So this is a learning tool that anyone can use. This is accessible to everyone. So a lot of the COVID research at the moment is scientific papers. And I'm a uni student and I read them and I don't understand. Just straight up, I don't understand. It's not my domain. So this is a tool so that anybody can access it. And then the last one is the well-being of everyone. So with that government policy implementation, it allows governments to implement policies that restrict the spread, but don't impact the mental and physical well-being of people so much. I don't know about all of you, but when we were in lockdown, I hated it. Right? I hated it. I would much rather other effects than lockdown. So the viability. So we used open source data for this. So the main ones were the Our World in Data coronavirus source data, so that's daily cases, and the Oxford COVID government response tracker. So that is when the day that a policy has been implemented. And we combine the two to make a model. And so the model is the total cases in a day, and that's modeled as a function of the cases from yesterday and which policies are in place. And the simulation also has some additive random noise, so it reflects coronavirus a bit more realistically with that randomness. The innovation, so as I said before, this is accessible to anyone. This is just a web app that anyone can access, but it's also scientific. It's backed by data and publicly available data so that anyone could recreate this. Scalability, so this goes both ways. So at the moment, it only works for about 100 countries. So we kind of had a bit of a cookie cutter model just in the time frame, and so those were the countries that fit that cookie cutter, but with more time you can expand that and make country-specific models so it works worldwide. And then you can also go the other way and go state-specific. So at the moment for Australia, for example, it's only for Australia-wide, but you could very easily drill that down to a state level. And where next? So at the actually I think we've got this one in, but the time lag. So there's obviously a lag between when a policy is implemented and when it's reflected in the data. So that works now. Immunization, so the ability to simulate the effect of a vaccine. So you can look at how effective does our vaccine need to be such that we can dramatically reduce our mitigation policies. Obviously increased to all countries worldwide, and also to a range of diseases. So this is coronavirus specific, but with the right data, you could expand this to things like the common flu. And so this is what it looks like. I'm going to flip over now to the actual app. Here we go. So as you can see, all the countries that are available are in green. And we can head to Australia, get some statistics, and we can set how many cases that we start with. And we can change our susceptible population. So if we wanted to simulate from today, our susceptible population would be less because there are people in Australia, less than the population, because there are people within Australia who have already contracted coronavirus. So it looks like this. So we can start the simulation, just stop that after a couple of days. Oh, it's broken. Okay, this is the one that works. So the time lag doesn't work on this one, but the rest of it should. So we can start the simulation. Yep, there we go. And so we can see on the left, we've got the total cases, and we've got two lines. We've got uncontrolled growth, if you didn't put any mitigation policies in place, and then your actual cases for when you do put those policies in place. In the middle is your new cases, so that will get spiky over time, and then on the right, you've got the proportion of your susceptible, infected, and recovered population. So if we scroll down here, we'll let it go a little bit. And we'll say we're going to restrict gatherings to less than 10 people. And we can already see that that has a dramatic effect. This is without the time lag. Dramatic effect compared to the uncontrolled population. Thank you.
And this is our student team, so pretty impressive, I would say. Questions?
My question, excellent, was going to be, oh, so you've made this then? And so the answer is yes.
Good on you. I think you should be talking to Dr. Norman Swan from CoronaCast immediately, or he should be contacting you.
What we found, the thing is, there's an absolute ocean of data on this stuff. It's really quite cool. We definitely can, that's a knob you can definitely tweak in the future. The other thing that we were really looking to implement further on is, if we go back to the map page just real quick, I'll show you, there were some quick stats on different countries. So Australia had like a population density and all these kind of things. So population density, 3 persons per square kilometre. What we've got that data as well. So what we're going to do is drill down to the level of, like, social distancing may be less effective in West Australia because our population density is way lower. But in New York, it's massively important. So we have that data, and it's basically just a question of extending the model and incorporating those bits and pieces into it, such that you can have something that's really quite potent, but also